Hi everyone. Today in this video we are going to discuss molecular orbitals of benzene. Benzene is a special compound with 6 p orbitals. These p orbitals can overlap to form pi bonds. So during this overlapping, these p orbitals can form either bonding molecular orbitals or anti-bonding molecular orbitals. So for the structure of benzene, how many molecular orbitals are present? And among them, how many are bonding molecular orbitals and how many of them anti-bonding molecular orbitals? Let us discuss all these things in this video. So if we consider the structure of benzene, it is having few of the special characters. This compound is aromatic in nature. Because of aromaticity, this benzene is highly stable. Due to delocalization of pi electrons, benzene is resonance stabilized and is having the resonance energy of 36 kilocalories per mole. And this benzene is having the 3 pairs of pi electrons. Totally it is having 6 pi electrons, exist as 3 pairs, which follows 4n plus 2 pi rule. And finally, the benzene ring is resonance stabilized. So during this overlapping, it can form both bonding molecular orbitals as well as anti-bonding molecular orbitals. Due to higher stability, electrons always present in the bonding molecular orbitals. But when we supply the energy, they can undergo transition such that they can enter into the anti-bonding molecular orbitals. So today in this video, we are going to see which type of molecular orbitals are present for the benzene and how they are going to be formed and how many bonding and anti-bonding molecular orbitals are present for the structure of benzene. All these things we will discuss in this video. So in order to see the pi bond formation, let us say a simple case of ethene, which is having the p orbitals like this. These p orbitals can overlap to form the pi bond. So they can overlap in this way such that similar lobes are interacting. Otherwise, they can overlap in this way such that the opposite lobes are interacting. In this way, ethene can undergo 2 types of overlapping. So it can go in phase overlapping, which can be indicated like this, where similar lobes are interacting. Since similar lobes are interacting, this forms a stable molecular orbital, and this is called bonding molecular orbital. Let us indicate this with symbol psi1. Similarly, when it undergoes out of phase overlapping, the p orbitals can overlap such that the opposite orbitals are interacting. So this is not a stable molecular orbital, so it is considered as anti-bonding molecular orbital. Let us indicate this with symbol psi2. In this way, ethene can produce 2 molecular orbitals. One is bonding and the other one is anti-bonding molecular orbital. Now we can represent these molecular orbitals in this way. The bonding molecular orbital forms a stable overlapping where the electron density can be observed above and below the sigma bond. This is the bonding molecular orbital. Similarly, the out of phase overlapping produces the p orbitals in out of phase, and a nodal region is observed in between these 2 p orbitals, which is less stable, and it is indicated as anti-bonding molecular orbital. So this is a simple example of ethene, which is having a pi bond in between the carbons, where the pi bond can be formed either by in phase overlapping or out of phase overlapping. In phase overlapping produces bonding molecular orbital, and out of phase overlapping produces anti-bonding molecular orbital. Now with this information, let us discuss the structure of benzene and how it can produce bonding and anti-bonding molecular orbitals. Benzene is having the 3 pi bonds. So it is having the p orbitals like this. They can overlap in different way to produce different types of molecular orbitals. In this configuration, we can observe that all the p orbitals are oriented in similar way. In the first pair, the p orbitals can overlap in this way where similar lobes are interacting. So this is a bonding interaction. Similarly, the second pair can undergo bonding interaction because similar lobes are on the same side. Similarly, the third pair can undergo bonding interaction. 4th, 5th, 6th. In this way, all the p orbitals can undergo bonding interaction. So in this orientation, all are bonding interactions. Since it is having 6 bonding interactions, this molecular orbital is highly stable. So we can represent this as a pi cloud above as well as below the ring, which is uniformly delocalized. So it is a stable bonding molecular orbital. So let us indicate this molecular orbital with symbol psi1, and it is a bonding molecular orbital. Now let us consider another orientation. Here you can see that 3 of the p orbitals are similarly oriented with blue colored lobes on above the plane, and other 3 p orbitals are similarly oriented with blue colored lobes below the plane. Suppose if we consider these p orbitals, they are having the bonding interaction. Again, these p orbitals are having the bonding interaction. So here we can observe 2 bonding interactions. Similarly, here p orbitals can undergo bonding interaction because of similar lobes, and again these two can undergo bonding interactions. So totally we can have 4 bonding interactions within this configuration. And what about the p orbitals in between these? Here these p orbitals can overlap such that the opposite lobes are interacting, so they can undergo anti-bonding interaction. Similarly, we can observe another anti-bonding interaction here. So now this orientation is having 4 bonding interactions and 2 anti-bonding interactions. Net effect is this molecular orbital is having 2 bonding interactions. Since bonding interactions are more compared to the anti-bonding interactions, this orientation forms bonding molecular orbital. Let us indicate this with symbol Psi2. Now if we see the benzene ring, the pi cloud is like this, above the plane and below the plane, but the pi cloud is not continuous because of anti-bonding interactions in between the 2 p orbitals. Even it is not highly stable as Psi1, still it forms bonding molecular orbital because of more bonding interactions. Now let us consider another orientation. So here the atoms and p orbitals are oriented in similar way, so they can undergo bonding interaction. Again, these 2 p orbitals can undergo bonding interaction. So here we can observe 2 bonding interactions, but in between these pairs we can observe some nodal region. This is the region where the probability of finding electron is 0. So within the nodal region we cannot observe any bonding or anti-bonding interactions. So this orientation is totally having 2 bonding interactions. So let us indicate this molecular orbital with letter Psi3, and this Psi3 is equivalent to Psi2 because it is having the 2 bonding interactions without any anti-bonding interactions. So it is equally energetic as Psi2. So if we see the benzene structure like this, it is having the pi cloud like this, and we can observe the nodal region between the pi cloud. And since bonding interactions are more, again it is considered as bonding molecular orbital. In this way, benzene can show 3 bonding molecular orbitals which are indicated with symbols Psi1, Psi2 and Psi3. Now let us consider the other molecular orbitals formed by the benzene. So this is one of the orientation where you can observe similar lobes are on opposite side. Suppose if we consider these p orbitals, they can undergo anti-bonding interaction. Again, these 2 p orbitals undergo anti-bonding interaction. Similarly, these 2 can undergo anti-bonding interaction and these can undergo anti-bonding interaction. So here we can observe 4 anti-bonding interactions. In between these p orbitals, we can observe bonding interaction because similar lobes are on the same side. We can observe bonding interaction. Again, on the opposite side, we can observe bonding interaction. So within this orientation, we can observe 2 bonding interactions and 4 anti-bonding interactions. So the net effect is this molecular orbital is having 2 anti-bonding interactions. Let us indicate this with symbol 5,4. And since anti-bonding interactions are more, this orientation forms anti-bonding molecular orbital. Now let us consider another orientation like this. Here we can observe 4 p orbitals are present and they are oriented in opposite way. So the first pair can undergo anti-bonding interaction and again the second pair undergo anti-bonding interaction. And in between these pairs, we can observe the nodal regions. So this molecular orbital is having 2 anti-bonding interactions without any bonding interactions. Let us indicate this with symbol Psi5, and this molecular orbital is isoenergetic with the previous molecular orbital Psi4, because in the Psi4 we have observed it is having 2 anti-bonding interactions. Again, this molecular orbital is also having 2 anti-bonding interactions, and since this structure is having anti-bonding interactions, we can consider this as anti-bonding molecular orbital. Finally, let us see another orientation. Here we can observe that all the p orbitals are oriented in opposite way adjacently. This pair shows anti-bonding interaction. Again this pair antibonding, this pair shows antibonding interaction. Again this pair antibonding, this is again antibonding, and this is again antibonding. So totally this orientation is having 6 antibonding interactions. So all p orbitals are undergoing antibonding interaction. So it is least stable molecular orbital. Let us indicate with symbol psi6. So this is the least stable anti-bonding molecular orbital. So if we summarize the benzene and let us see the energy diagram, how these molecular orbitals are oriented. The first one is the psi1, which is highly stable, having the least energy, and electrons can exist on this psi1 molecular orbital, which is highly stable and less energetic. Then the second molecular orbital is the psi2, where it is having 2 bonding molecular interactions. Similarly, another one is the psi3, which is isoenergetic with the psi2 with 2 nodal regions. So electrons can present in both of these bonding molecular orbitals. Similarly, another one is the psi4, which is a anti-bonding molecular orbital with 2 anti-bonding interactions. Another molecular orbital is psi5, which is isoenergetic with the psi4 with 2 anti-bonding interactions and 2 nodal regions. Under ground state, electrons will not present on these anti-bonding molecular orbitals. But when we supply the energy, they can jump from bonding molecular orbitals to the anti-bonding molecular orbitals by absorbing the energy. And finally, we can see the psi6, which is the least stable and highly energetic anti-bonding molecular orbital. In this way, the benzene can show 6 molecular orbitals. Among these, 3 are bonding molecular orbitals and 3 are anti-bonding molecular orbitals. So that's about the molecular orbital theory of benzene. Benzene is highly stable because of resonance stabilization. So electrons can present in the psi1, which is the highly stable and less energetic bonding molecular orbital. So in our next video, we will come with another interesting topic. That's for today. Hope you have enjoyed this video. If you like this video, please subscribe to our channel, share this video with your friends, post your comments in the comment box. Thank you for watching this video.